Hello and welcome to MEL Science. Lovely to have you all on board. Lots of little smiling faces. Lovely, lovely, lovely. I'm just going to change my screen so I can see you all, or try and see as many of you as possible. Who are we? What have we got here? We've got Noah, we've got Abby, we've got Karen, we've got Charlie, we've got Lily, we've got Kiara, we've got Chanel, we've got Vanessa, we've got Avery, Mackenzie, Heather, Sarah, hang on, I've got another thing I've got to click down here. Claire, Connor, Aria, I think. Some more people coming on board. It's all chaos at the moment. Lovely, 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 lovely. How wonderful to see you, and thank you once again for joining us here on this little session with chemistry at MEL Science. So great. Don't worry if you don't want to reveal your video. You can actually say contact me in chat, and I'll try and remember to contact chat. If you are using chat, please remember. So I look at all the sort of the videos and sort of the live streams, and I sometimes miss a chat. But you can just keep hammering the questions, and I will get to you. So Connor, thank you very much. Connor, good, cool. I think everybody's in there. Right, without much further ado, let's just quickly focus on the kit that we're going to do today. And of course, it's the rather magical Egyptian nights. We're from Boston. Hi, Kiara. Lovely to have you in Boston. It'll be Boston afternoon. It's about 10 o'clock here in the UK. So I'll just switch focus on the tabletop just to go through the kit that we need. So today we're going to do the Egyptian nights. So this is the set we're going to go through today. So in no particular order, I was going to go through the equipment that we actually need for this experiment. So first things first, you do need access to some hot water. So I've got a flask here. So this is boiling water, okay, folks? So you need access to some really hot water for this one. So this gives you opportunity to nip off and quickly boil a kettle. Do I need noodles? Una, you do not need noodles. These are... So this is for demonstration purposes. This will all become really clear, okay? You do not need noodles. This is just for demonstration. But you do need, if you want, the two cards. This shows you the experiments that we're going to cover today. Right, what else do we need? We need a conical flask. So make sure from your starter kit you've got the conical flask. You need 2 of your little tiny plastic beakers from your starter kit. Also, you need a glass beaker. So your glass beaker. Also glasses, so safety specs. You need your gloves, so a little pack of gloves. Now, in no particular order here, the stickers. Now, I don't have particularly long fingernails, so I'm going to use a little tweezer to make peeling these stickers off a little bit easier. But if you've got nice long sharp fingernails, you won't need those at all. So stickers. Right, so we also need, 2 of these little tiny Petri dishes. So 2 Petri dishes. The black piece of paper, that's purely for comparison. Pipette, some of these scoops, measuring scoops, the little tiny pin, obviously to pick the little safety plug out of the reagent bottles. You also need the little tiny thermochromic sticker, and the chemicals, ladies and gents, the chemicals we need today. So first chemical here in the room is sodium hydrogen sulfate. So that's sodium hydrogen sulfate, that's the first chemical. And a potassium iodide is the second chemical, so Ki, potassium iodide. We also need the starch. Now this is soluble starch. Starch as a molecule isn't terribly soluble, but this one is very soluble. Then we need the sodium thiosulfate, this kind of orangey yellow colour one, so the sodium thiosulfate. And then last but not least, we need the iron chloride. So this is the iron chloride. Okay, have I forgotten anything, Dan? Have I forgotten? Oh, yes, and some cold water, some just tap water, some access to some tap water would be amazing. Okay, I think I've got everything. I think I've covered everything. Is that okay? Is everybody ready to start? Yes? Everybody got some thumbs up? Yeah, you don't actually, that you see is one of the most effective ways of telling me things are okay. Stick a thumb up or go, no, like the sort of Roman Senate or anything like that. Okay, so thumbs up and thumbs down is great, or you can chat, and that's it. I got a load of thumbs up, which is remarkable. So, okay, so very, very quickly, it's Egyptian nights. So this is a side show, Egyptian nights, etc., etc. And just before we begin, hopefully this will work for me. I'm hoping this is going to work for me. Look, it's Egyptian night. But you hadn't seen that before, okay? It's all very dark in Egypt at night. Okay, so little jokes aside, let's get back to the chemistry. So 10 o'clock effects. Right, so stick, if you will, your gloves on. So put your little gloves on. And what we're going to do first, we are going to do the one called sulfur moon. So the sulfur moon is the one we're going to do first, okay? So I will then move some of these reagent bottles around so we've got the right ones in place. Right, if you have got sharp little fingernails, then now's the time to peel off 2 little stickers from your little sticker board and stick it into the base of your 2 little Petri dishes. Okay, so stick that into the base of your 2 little Petri dishes. Now the chemicals we need for this are the sodium hydrogen sulfate. So I've got sodium hydrogen sulfate, the sodium thiosulfate. So these 2 chemicals are the ones we need for this one. Okay, and you need access to some water. So I'm going to just move the rest of these chemicals to one side and the pipette. Then I'm going to just keep some spoons here, so 2 spoons. We don't need the thermochromic film. Right, so before we begin, I just want to show you a quick reaction. So this is just a demonstration, and I want you to remember what I'm doing, okay? Remember what I'm doing. So here, look, I've got some bread, I've got some rice, I've got some potato, I've got some pasta, and I've got a slice of lemon. I've also got some what's called Lugol solution, sorry about the bottle, but Lugol solution, which is iodine solution. But look what happens to the colour. Look what happens to the colour of these foods when I put iodine on them, okay? So just watch this carefully, So the iodine is a kind of browny colour, but look, if I put some iodine on the bread, and then iodine on the potato, iodine all over the rice, put a bit more on the rice, and then iodine on the pasta, little iodine on the pasta, sorry. And then finally, a little bit of iodine on the lemon, just to show you. What colour is the iodine making those foodstuffs go? What colour is it? Anybody tell me? Yep, hands up, we've got a hands up. Yes, let's go for it. Abby, yes, Abby. Una says black, asked to unmute. Can everybody see that? I hope everybody can see that. Asked to unmute, yes. Abby?
Red for the lemon and black for the rest of them.
Cool. Now, I'm just checking that. So it's important for me to see that and for you to know. Yeah. Actually, it might look red, but that's actually a brownie. It's a dark brownie colour, okay? And that's actually the colour of iodine here. But everything has gone black, okay? Everything has gone black. I just want to just quickly recap on that one. Right, so just remember, when you put iodine on starch, it goes black, okay? So that's a little quick demonstration over, and that will make sense, I promise you, in the last experiment, okay? On the bread and rice, yes. What substance did you dip again? Connor, I put in iodine solution, okay, iodine solution. Right, so let's get back to the first experiment. So the first experiment, look, is the sulfur moon. So what you do, look carefully, is stick 2 stickers in the base of your little Petri dishes. So I'm going to stick in a little palm tree into the base of one. So it's a white palm tree into the base of one. I'm going to move that sulfur moon out of the way, so I'll bring that camera a little bit closer for you all to see. And move those 2 out of the way. And now I'm going to stick another little sticker onto the base of the other one. So this is a little tiny snowman. Hopefully if I can get the snowman out of its little perch in the sticker pad. Hang on. Almost there, and there we go. Cool, so there's my little snowman. So there's a snowman. You can use any sticker you want, so you don't have to use any particular one. So any one there. Look. Okay, cool. Now what we need to do with one of your cups, okay, we need some water. So if you just put some water into a little cup like so. Okay, so I've just put some water into a little cup like that. And what we need to do now is using a spoon. So this is the spoon, just to take the right sort of measure. You want 2 spoons of water in one of the Petri dishes. Okay, so 2 full spoons, that's one, look, in one of the Petri dishes, and then the same second spoon in the same Petri dish, okay? You might just roll that around a little bit so it's full. So one of the Petri dishes has 2 scoops of water, okay? Oh, I've got a hand up. Hang on, let's go to the hand. Una, asked to unmute. Una, yes. Go for it.
was going to get water.
Oh, no problem. Una, it's this big one. It's the big one. So the big one. Yeah, is that okay?
Okay, thank you.
You're very welcome. It's a pleasure. Admit Amber to the room. Yes, Amber, you're in. Ask, yes, Kiara. How are you doing, Kiara?
I'm doing well. Is it hot water or room temperature?
That's room temp. For this one, it's room temperature water. So for this one, it's room temperature water.
Okay.
And I think that answers your question, Lily and Sergio. I think that's just normal water. Yeah. Okay, cool. Right. So next, using a big scoop, and the chemical we want here is the sodium hydrogen sulfate. So the sodium hydrogen sulfates, that's the blue label. Now we need, if you haven't done it already, of course you need to take this safety plug out of the thing. So what you do, of course, is you take your little paper clip here and then give that a little poke, fairly firm poke, because sometimes they can be a bit stiff. Yep, there we are. So give that little poke. So take the safety plug out of the sodium hydrogen sulfate, that is, and put one big scoop in the one with the water already. So one full scoop, like so, in the one with the water already. Okay, so pop that in there like so. And you can just give that a little tiny shake around. So just give that a little shake around like so. So that mixes up those two solutions. Now, my second one that's got nothing in it so far, you're going to put, again, one big scoop. Okay? So one big scoop in that one with nothing in it so far. Okay? And then put the lid back on your reagent bottle. So put the lid back onto the reagent bottle. So far, folks, nothing has happened. But now we are going to react two separate reagents. So the second reagent we now need is the sodium thiosulfate. So this is the sodium thiosulfate. So again, take the lid off this one and depress the little tiny safety plug out to the top of the bottle. Again, giving it a little... So sometimes, again, guys and girls, it's a little bit stiff. So this one's proving a little bit resistant. I think we'll get it, yes. Poke, poke, poke. I think we've almost got it. And then it goes. So there it goes. Good to know that they are very effective, these little seals, at keeping those chemicals in the reagent bottle. That's one. Yeah, excellent. Right. So with another scoop, you're going to put, listen carefully, one scoop in the Petri dish that's got the most fluid. So this Petri dish with the 2 scoops of water and the 1 scoop of sodium hydrogen sulfate, you're going to put one big scoop. Okay. And watch carefully as you do this. Okay. And in the other one, the one with only 1 scoop of anything in it, you're going to put 3 scoops of the sodium thiosulfate, okay? Now, as soon as you put that 1 scoop in, you should have seen some bubbles forming immediately. 1, 2, and 3. Now, watch carefully. You should be able to see, strangely, it's going white. It should look as though it's going white. And bubbles seem to be appearing on the bottom. How very odd. I'm going to raise this up for you. So hopefully you can see that. They're both going a strange kind of yellowy colour. And it's also beginning to smell a tad. Okay, I've got a hand up. Yes, a hand went up. Una says hand. Hang on, I'll just... where are you? Una, yes, go for it.
I'm actually curious, what chemical, I didn't see what chemical you put in to make it bubble.
Oh, the chemical I put in to make it bubble was the sodium thiosulfate. So Na2. Yep, that's the one. Perfect. Absolutely perfect. Yep.
Thank you.
You're very welcome. You're very welcome, of course. Okay, cool. Now, has everybody got some curious yellow bubbly mixtures? And does it smell rather badly? Is it? We have smells. You're not doing chemistry unless there's a smell in the room, okay? So hopefully, fantastic. Got some thumbs up. Mackenzie's got thumbs up. Isaiah says that Abby's wafting away. Yeah. Una's, yeah, cool. Excellent, absolutely excellent. Right, so we need to explain a little bit about the chemistry of this. So the bubbles The bubbles are sulfur dioxide. That's a really nasty chemical, but you've only got a few of these little bubbles, okay? So actually when they burn coal and they burn oil and petrol and diesel, stuff like that, one of the nasty gases that comes out of burning fossil fuels is that gas, sulfur dioxide. And actually when that goes up into the atmosphere, it creates acid rain. So this is not a nice chemical, but it's an interesting, the bubbles seem quite contented, don't they, in that little soupy mix of yellow. The yellow is actually elemental sulfur. So when we saw this one, for example, the sodium thiosulfate, the S in there, the S has become free sulfur as well as bonding to the sulfur, the oxygen to form sulfur dioxide. Okay, and that's coming out. Now, the critical question, did those reactions take place at the same speed? Or was one slightly slower than the other? Anybody know? Abby says kind of. Anybody else? I'm using the smaller kit that just says one. Charlie, no problem, Charlie, no problem, no problem. You should have noticed that one of them was faster than the other. And actually, that's because it's more dilute. It's actually more dilute. And actually, one of them's got a little bit more sulfur in it, okay? Now, that's because in this particular chemical set, we're looking at what's called rates of reaction. All chemical reactions take place at different speeds. Have you noticed that when you take a tablet, for example, for a headache, does your headache go immediately, does it disappear immediately? Woof, disappeared. No, it doesn't do that, okay? But happily, when you put petrol in a car, okay, the petrol doesn't go, oh, burn! It runs really quickly, okay? And that is because these chemical reactions take place at very different speeds. Okay, let me just quickly nip onto a slide so I hope there's a question. No, the one that smells was the one without water. I got rid of the smelly one. Heather, that's fine, that's fine. If you don't like this smell, now this smell can get a bit irritating. If you don't like this smell, okay, all you've got to do is take those little containers and wash them with some warm running water, and that'll get rid of it and stop the reaction altogether, okay? So you can do that if you wish. Okay, so let me have a quick look at this slideshow. So here's some Egyptian night. Just kidding, I'm just kidding. Okay, why is it called sulfur moon, this particular thing? Well, actually, sulfur is an incredibly important element. It's the 8th most important element in your body. Every one of you, the 8th most important element in your body is sulfur. So you've got lots of sulfur in your body, lots of it. But if you go to the moons of Io, for example, in Jupiter, they're actually sulfur volcanoes that throw up massive plumes of molten sulfur and gaseous sulfur dioxide, okay? So out near Jupiter, you've got this really incredible reaction going and throwing up sort of, massive plumes of sulfur. So that's why it's called sulfur moon, because it's the Io, the moon Io of Jupiter. Okay, so what's actually happening there? In basic terms, you've basically got atoms that are stripping electrons from something and taking electrons from other. You've got a basic chemical reaction that's producing sulfur dioxide and raw sulfur as a precipitate. And that's why that little image that you have in the bottom has now disappeared under this precipitate of solid sulfur. Was that okay? Was that okay? Cool. I'll go on to a bit more of the chemistry a little bit later, but what I'm quite keen to do is get back to the second reaction, okay, so the second bit of chemistry. Are you all ready for the second chemical experiment? Yes, we're all good. Yes, excellent, excellent, wicked. So for this one, you need your hot water, okay? So you need your hot water. So I'll just switch back to tabletop with face. Tabletop with face, I'm going to move these two out of the way. Okay, and move that one out of the way. Now, ladies and gents, you've got to be careful with this one because you've got to watch it really carefully. It does something really amazing. This one does really amazing stuff, okay? So what we want, first of all, is our conical flask. So you want your conical flask. You also want a beaker. So one of these little plastic beakers, and the first chemical we're going to use is starch. So the first chemical we're going to use is starch. And this is where you want the hot water, okay? So if you get another spoon, you want one big spoon of starch in to the beaker. So one big spoon of starch into the beaker. Whoops, like that. If it's a little bit over, a little bit under, don't panic at all. So one big spoon of starch into that beaker. from volcanoes. Connor Huang, yes, it was from volcanoes. Yes, on Io, they are from volcanoes, yeah. And actually on Earth, you also get lots of sulfur associated with volcanoes on Earth. Okay, right, so once you've got that spoon of starch in your beaker, you then put in some hot water, about 100 mils, about 50 mils to 100 mils, okay? But before we do that, of course, it's very hot water, so we actually need one of our stickers, our thermochromic film, okay? So if you pop your thermochromic film onto your, I'll just take that off. So pop your thermochromic film onto the little beaker like that, okay? So that tells us health and safety wise that it's going to be really hot. So we're going to pour, look, about 50 mils, 100 mils into the beaker like that. And then you need to give that a stir. So with our little tiny stirrer, so give that a little stir. Now starch isn't massively soluble, but this one has been fiddled around with, let's say, to make it a little bit more soluble. Normally starch isn't terribly soluble. Okay, so just, and if you've got little lumps forming, something like that, just give it a little prod. Okay, don't worry if it all hasn't dissolved. Don't worry if it all hasn't dissolved. You're just making a kind of starchy solution, which, by the way, is the chemical present in all the foodstuffs I just added a little bit of iodine solution to. Okay, so just give that little stir for about 30 seconds. Little countdown now, think about 10. Ah, Bean, I've got a question. Bean, go for it. Hi, asked to unmute. Bean, hello. Hello? Bean, you got your hand up, but you're not asking me a question. Ah, yes.
Was it one big spoon of starch?
Yeah, just one big, yeah. And don't worry if it's level or just slightly over that. Don't worry at all. So just one big spoon. Yeah, that's perfectly fine. Is that right?
Okay.
Lily, yes, it's just starch so far, Lily. Yes, it is. Yeah, just starch so far. Okay, cool. And then I'll just switch screen so everybody can see. Okay, so next, what you want is your pipette, and you want one whole pipette, so one full pipette into your empty conical flask. So with the starch solution you've just made, take one whole pipette solution, okay? Now there's a little trick, ladies and gents, so if you just put a little squeeze like that and you've got an air bubble in it, just hold the pipette up a little bit like that, and then give that a little squeeze, and you can put it back into starch solution and suck a bit more up, or draw a bit more of that starch solution up. Again, you can put a little bit more at that, and then suck a bit more up. So you want a one whole starch solution and put that whole pipette into the conical flask. Okay, so one whole. I'm going to just add a little bit more starch solution, just a little tad more, and add that in there like so. And remove that little bit of unreacted starch. So now what I've got in my conical flask is one pipette load of the starch solution. Okay, so one pipette of the starch solution. Now, this is where it becomes very important. So watch carefully. Oh, hang on, I've got a question. Una, ask to unmute. Hi, Una.
I'm not sure whether or not I put too much in. Like, is this too much?
Oh no, that's perfectly. Now your reaction might take a little bit longer. So if you just pour a little bit of that out, is your starch dissolved? More or less.
Not all the way.
Not all the way.
Not all the way.
That's fine. That's fine. But just pay attention to this one carefully. Okay. So your reaction might take a little bit longer. Okay.
Okay.
Okay. Cool.
That's fine.
No problem. Don't panic. Right. So back to the screen. So now, ladies and gents, we need the sodium thiosulfate. Okay, so the sodium thiosulfate. Okay, so orange one, and we need 10 drops of that into your conical flask. 10 only drops into your conical flask. Okay, now I've got a little bubble on the end of mine. Right, so 10 drops. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 drops into the conical flask, and give that a nice little whirl around, okay? So I'm just going to give that a little whirl, so give it a nice little mix around, okay? So I've got 10 drops in there. Now, the next chemical that we need is the potassium iodide, okay? So the next one we need is potassium iodide. So again, you're going to need to depress the little security plug out of the potassium iodide bottle, so it's a liquid potassium iodide. And for those paying attention to the bottle, you'll notice that it's 10 mils of a 2 molar solution. So it says 10 mils of a 2 molar solution of potassium iodide. So again, just give that a little wiggle to get that out. Right, so here we want one, I'm going to use a clean spoon for this one, so brand new clean spoon, one full scoop of the big scoop of the potassium iodide, okay? And pop that into your conical flask as well. And then put the lid back on your reagent bottle. Okay, now give that another little swirl around. So give that a nice little swirl around. Okay, so nice little mix. I'm just going to stop there just for a second to make sure everything's okay. Is everybody kind of okay? Got some thumbs so I can see that everybody's more or less okay. You guys okay? That's fantastic. Lovely, 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 lovely stuff. Okay, cool, cool. Right, now what we want here is take your glass beaker and you want 100 mils of just normal water, 100 mils of normal water. So this is room temperature water, 100 mils. I'll just fill that up so you can see. Okay. So that is normal temperature water, so room temperature water. That's 100 mils, okay? Just make sure everybody's got that. And now, using another spoon, I'm just going to give my one a little wipe here. Let's give him a little wipe here. We want the last chemical here. So this is the iron chloride. So if you identify the iron chloride, okay. And again, as always, depress the little tiny security plug in the iron chloride. Push that down. That went in much easier that way. Much easier that way. Okay. Now you put one big scoop. This is the iron chloride, of course, here. One big scoop into the water. So one big scoop into the water. Okay. So one big scoop into the water. Into the beaker. Okay. So one big scoop. Hang on. There we go. So one big scoop of the iron chloride into the water. And if you use the other end of your little spatula, you can just give that a little stir to make sure that it's nice and dissolved, okay? To make sure that's nicely dissolved. So I've got here water, room temperature water with iron chloride, one scoop of iron chloride. And here I've got all the other agents here, including the starch. Is that okay? Yeah? Cool, cool. Got some thumbs up. Right, now ladies and gents, this is where the magic is about to take place. And it happens really quick. I'm just going to change screens a little second, just for a second. This can happen really quick. So when you we're going to add all of that iron chloride solution to our conical flask. And what you need to do is watch really quickly, watch carefully. Sergio, nice effects, Sergio. Do like that a lot. Excellent. And that's because your screen, of course, is the same colour as the object you have there. Excellent. Okay, so watch very carefully. Okay, watch very carefully. Watch. So you're going to add this really carefully to your screen, to your conical flask. And then hopefully, watching it carefully. Bang! How magic is that? How lovely is that? That is a lovely piece of chemical wizardry if you like. So I hope you're watching it carefully. Now I think, Una, yours might take a little bit longer. Cool, yes. Lily, awesome, absolutely awesome. Kiara, I hope is okay. Abby, how are you doing? Aria, you got a question? Ask to unmute. Aria, yes, go for it. Aria. Oh, Abby's got one. Lovely, Abby, perfect. Isaiah, success. Yes, Aria.
Like right when I was pouring mine, it just happened. Like right when I was pouring it just happened really quickly.
Aha. Now that Aria is one of the tricks with chemistry is if you're not absolutely precise with how you mix the reagents and not exactly accurate, and you can be really careful. Okay, you can be really careful. But sometimes if you get like one drop too much or one drop too much here, sometimes the chemicals go, whoop, bye! And that's just the very nature of chemical reactions, okay? So there's plenty of, you can do this again plenty of times, okay? But if you do it again, you've got to make sure that you wash out everything really carefully. Is that okay? So don't panic, don't panic. That's what being a chemist is about. Try again. Sergio, how have I done this experiment? Cool. I've done this experiment. All right, cool. Yeah, nice one, Sergio. Yeah, this is lovely. This is a lovely experiment. So glad you enjoyed that. If I could just go back to the slideshow very briefly. Just a whistle-stop tour of some of the chemistry. Basically, all chemicals, all chemical reactions have different rates, and you can affect the speed of different chemical reactions with different properties. So concentration, temperature, catalysts, pressure, all of these different things can affect the speed at which chemical reactions take place. Now, you notice this chemical reaction here took place real quick eventually when poof, it suddenly changed. So why was that? We'll come on to that in a second, okay? And effectively, all chemical reactions take place because you've got colliding particles. So all the different molecules and atoms whizzing around and they collide. If they collide at the right speed and in the right way, then you've got a chemical reaction taking place. Okay, so if I just move past that one a little bit, just very briefly to bring Egypt back into it. This is an incredible culture, and the reason it's called Egyptian nights, of course, is because when you're that close to the equator, okay, the nighttime, you know, if you're in the north of America, or if you're in the UK or the northern part of Europe, the night, it starts to get dark, and then it gets dark, and then it gets dark. From maybe 4 o'clock to 5 o'clock in the wintertime, it gets dark and dark, and then by 7 o'clock, it's really dark, and that's it. But in Egypt, at about 4 o'clock, it starts to get a little bit dark, and then by 5, dark. Okay, so the closer you are to the equator, the nights quickly appear, very quickly. Okay, so that's why it's called Egyptian nights. And of course, Egyptian culture is full of history, lots and lots of stuff about history. Right, just to explain why did that happen? Oh, I've got to let somebody, Katrina, into the room. So what actually happened here? Well, did you see when if I just change my screen a little bit to show you the tabletop, if I bring my food back in, okay, so here look, as soon as I put the iodine onto the, just move that out of the way a little bit, just put that forward. As soon as I put the iodine onto the starch, it went black immediately. Now, in the vessel there, you had starch, and it was sort of floating around, and it was waiting for iodine in the potassium iodide, okay, so it could react and form this black substance, and we're going to come on to that in a second. But in the whole mixture of things here, in order to form the black compound, you had to have the element iodine present, and iodine was not present as an element, it was present as an ion, okay, charged particle, had too much charge on it. So the thiosulfate, okay, was very friendly compound, and the iron chloride is a very nasty compound. So what the iron was doing was snatching the electrons from the iodine. It went, oh, I want to be an iodine atom. And the thiosulfate was going, here, have an electron. So the iron was snatching the electron, the thiosulfate was giving the electron. Snatch, give, snatch, give, snatch, give, snatch, give, snatch, give, snatch, give. But there was only so much thiosulfate and only so much iron. So at a point, they all ran out of the ability to give and take electrons. At which point, iodine was in the room, and the iodine went hold of the starch and went flack. And you saw that immediate change point. As soon as iodine was available to hit the starch, it went black. And look, ladies and gentlemen, just one last... Oops, sorry. Last couple of slides. Here, look. I'm hoping that's going to work. Go for it. So what was actually happening, look, is the starch reacts with the iodine reacts with the starch to form this thing called a clathrate. So that clathrate, and that's the black thing that you see, that's a black compound that you see, and you saw it on my bread and the rice and etc. Okay, but you didn't see any iodine clathrate forming on the lemon because there's no starch in a lemon. Okay, and by the way, that's what Egyptian nights really look like. That's what they really look like, okay? And before we come and end the show with hopefully some questions, some Q&As, I've got a little joke for you. Would you like to see a little joke? Anybody up for a joke? Cool. This is one of my favourite jokes, okay? So I hope it's going to produce a little bit of mirth. What do you call a pharaoh that hunts whales with a folding bed? Futon harpoon. Well, for those of you maybe don't understand the joke, who was one of the most famous of all of the Egyptian pharaohs? Who was the most famous of the Egyptian pharaohs? Yes, Abby, asked on mute. Who was the most famous of the Egyptian pharaohs? Abby.
King Tut.
Correct, King Tut. Tutankhamun. Rhymes with futon harpoon. Anyone knows? You kill a joke if you explain it sometimes, who knows? Hey. Right, any questions? Was that fun? Was that fun? Cool. Excellent. Right, have you guys and girls got any questions? Lovely to have so many of you here today. Have you got any questions for me? Charlie, perfect. Charlie, yeah, looks okay. Looks okay.
What's your question for you?
And yes, Abby.
My question is, how come Egypt, when it's 5, it goes super dark?
Oh, it's to do with the two things. It's a lovely question, Abby. It's two things. Okay, it's to do with the orientation of the Earth and its position, okay, around the sun. And if you are close to the equator, it means that the sun rises and the night and day fall quicker because you're very much closer to the sun. Well, it's not close to the sun, sorry, take that back. It's just you're angled directly to the sun. Whereas if you are closer to the north, you're up the northern hemispheres, okay, or even in the southern hemispheres, the daylight rises, the dawn rises much, much more slowly, and the nighttime creeps in much more slowly. Okay, so when you're at the equator, dawn, and then at nighttime. Okay, so closer to the south, the north and the south, and the dawn rises much more slowly. And then, is that okay? Cool. Lily, you're very welcome. Lily, go for it.
So what happened to our experiment? So we poured in the thing, and it turned brown, and then it turned white, and then it turned black right away.
Yeah, and that's lovely observation, lovely observation. So when you poured it in, so some of you may have seen that the solution went slightly brown to start with. That's because it's slightly brown to start with means that some of the iodine was actually in solution as iodine molecules, okay, and you can see that brown. And so it just occasionally appeared. But then it went white, and that's where that reaction of taking electrons and giving electrons and taking electrons and giving electrons was actually established in a nice kind of way, okay, a nice balance, okay, and that got rid of the brown, that got rid of the iodine. But as soon as that giving and taking of electrons stopped because the reagents ran out of the ability to do that, the iodine went, yippee, I'm here! And then it bumped into its friend and went, oh my gosh, there's starch here! Bang! Okay, and react with the starch to form the clathrate. Is that okay? Cool question. You're very welcome. Any other questions? Abby, yes, asked on mute. Abby, go for it. Yes, asked on mute. Yeah. No questions?
Sorry, I had just put a thumbs up.
Oh, right, okay. Thank you very much. Okay, cool. Una, you got a question? Yes, go for it. Asked to unmute. Una.
Mine did something different than what they described. Mine turned yellow, like very light yellow, slowly.
Yeah.
And then a little tiny bit of like dark brown appeared, and it started going darker and darker. And it was like right in the center.
Yeah.
And then like a moment later from that happening, it like spread out and
poof. Right, do you remember that when I said when you put all the different reagents into the conical flask, I said give it a stir each time, so give it a swirl around each time. That's in order to make sure that you've mixed all of the different reagents properly. But if you didn't do that properly, you'd have concentrations. You know, like for example, you know when if you want to make a glass of squash, yeah. You put in some water, and if you just poured into the undiluted squash, and you didn't do anything, there'll be parts of it be very concentrated with squash and then parts that are not, yeah? So those chemicals, those reagents, those molecules have to spread out and diffuse so it's uniformly concentrated. And what you had there was some of the reactions in some parts of your conical flask could go, oh my God, there's so much chemicals here. And then other parts are like, oh, there's hardly anything here. But eventually they all started to react, and that's what happened in your case. Is that okay?
Mm-hmm.
Cool. Kiara, yes, asked to unmute. Kiara, go for it.
In the self-renewing experiment, when you put the sodium thiosulfate in, why does it turn yellow?
So in the second experiment, sorry, you broke up a little bit. So in the
first one,
yes,
when you put the sodium thiosulfate in, the orange chemical,
that's right.
why does it turn yellow?
Oh, why does it turn? So when you look at the molecule, when you look at that bottle, let me find the bottle again. So when you look at this bottle, the sodium thiosulfate, if you look at the chemical, can you read the chemicals? It's got sodium, Na, so that's the metal, sodium. Then it's got S, which is sulfur, and then it's got oxygen, so O thing. Now, so when all those chemicals are bonded together nicely, they form that solution, sodium thiosulfate, which is a colourless solution, okay? But one of the magical things about chemistry, you know, don't you, that oxygen is a colourless gas, yeah? You know, or you might not know, that sodium is a metal. It's a shiny, silvery metal. And sulfur, I'm sure you might have seen volcanoes, and the sulfur coming out of volcanoes is a yellow, non-metal solid. Now, strangely, when you react the sodium and the sulfur and the oxygen and go, kazum, you get a, well, actually, you get a white crystalline solid, but then you drop it into some water and you create a colourless solution. But the sulfur, the yellow sulfur, is still there. Okay? It just wants to reveal itself. So what happened in that reaction, when you reacted it with the sodium hydrogen sulfate and the sodium, what happened is that sulfur was able to go, oh, I'm free! And it came out as elemental sulfur once again, and that's why your solution was yellow. Not all of the sulfur, of course, became the yellow, and it's very, very insoluble largely. But it also reacted with a little bit of the oxygen in that compound to produce the sulfur dioxide, which is that horrible smelly gas that came out. Is that okay?
Okay, thank you.
You're very welcome. An absolute pleasure. Hi, Bean. Asked to unmute. Bean, go for it. Sergio, between us. Thank you very much, Sergio. That's very pleasant. Much appreciated. A delight. I'm sorry, I can't also answer everybody's question at the same time, but I appreciate that. Thank you very much. Bean, go for it.
Okay. Is it okay if you leave?
Yeah, of course. Stay as long as you wish, or as short as you wish. It's just to hear someone's question. But thank you very much for subscribing to MEL. Thank you for joining, and I hope maybe see you tomorrow or next week. So have a lovely afternoon and great week.
Thank you very much.
It's a pleasure. Absolute delight. Yes, Abby, asked to mute. Abby, go for it.
Does it actually, just go black that fast?
Yes, yeah. This reaction, if you go after the webinar, if you want to check on YouTube and go clock reactions, okay, clock reactions are very famous type of reactions in chemistry, and some of them are really weird. Some of them go backwards and forwards, and they actually switch backwards and forwards, okay? And in one of the MEL kits, the oxygen kit, when you do it, it's one of those reversible clock reactions. So you can investigate those and have a look at your own time. Is that okay?
And I also have one more question.
Sure.
What is squash?
Well, sorry, of course, I'm obviously fairly British. I'm not sure what you call it in the US. You know when you get a concentrated solution of like a juice? Sorry?
In Canada.
In Canada. It's like, you know, if you get like strawberry, it's like a cordial, it's a squash, it's something you have to dilute. It's really concentrated sugar solution with a flavour, and then you have to add water to make it a drink. Yeah, you couldn't drink the actual concentrate because it's too sticky and sweet and sugary. Have you ever noticed if you go and order some Coca-Cola or something like that from a fast food vendor, and you look at the streams of liquid coming in, first of all the concentrated liquid comes in like a quick squirt, and then that's followed by a stream of water. Yeah? So that is the kind of, I don't know what the word is in Canada. Cordial, squash?
What would it be?
I don't So there you are. If you go,
I know what he means by the syrup, but
it's a syrup, yeah, like a concentrated flavoured syrup, yeah. We get there in the end. We got there in the end. Lovely. Right. In which case, if there are no more questions, I would like to say thank you very much for subscribing to MEL. I hope that's been useful. I really look forward to seeing you again sometime. I hope you learned some chemistry. I hope that was okay. I didn't think the joke was too bad. In which case, have a great weekend. Oh, you've got 1 day, or 2 more days. Have a great week and a lovely weekend. Stay safe and stay well. Thank you very much. Goodbye.